Hello, everyone. My name is Kannan Muthukkaruppan. My pleasure to welcome you all to another episode of YugabyteDB Friday Tech Talks for engineers by engineers. And today I have with me John Meehan. So would love for him to introduce himself, and he's the main speaker for the topic today. So John, why don't you go ahead maybe with this short introduction, and then you can introduce the topic and keep going.
Okay, thanks, Kannan. Sounds good. My name is John Meehan. I've been at Yugabyte for a little over 2 years. I'm on the DSD team and largely work in the storage level, specifically as pertains to disk usage and compactions. And so today what we're going to be talking about is some recent additions to compactions and how we can detect them, detect when a full compaction may improve read performance. So just to orient the talk a bit, if we have the layered architecture of Yugabyte, what we're looking at here is like a single node of YugabyteDB, and specifically we'll be looking at the storage level and the RocksDB instances in particular. So RocksDB, essentially you can think of a one-to-one mapping between RocksDB instances and tablets. It's not perfectly accurate in the case of YSQL, but for the purposes of this talk, you can think of one tablet equals one RocksDB instance. And so that's the level we'll be discussing here.
And just for context, a tablet is just another word for, think of it as a shard of a table. So, and we have both cases. Sometimes a single large table can have many tablets. And like what John was alluding to with YSQL, we also allow sometimes multiple tables to be packed inside the same tablet, and that use case is like, we call it the co-located tables. Go ahead, John.
Yep, and so just to give an idea of the life cycle of a write to DocDB, essentially writes first get written to mutable mem tables, which become immutable, and then eventually get flushed to disk in the form of immutable SST files. And so it's that level that we'll be focusing on, is what happens with those SST files after they're on disk. To manage SST files, what we use is compactions. So we have what's called automatic background compactions that happen in DocDB that get triggered in a couple of different ways. But essentially, you can think of them as combining files into one larger file. So after a number of flushes, those files get combined into one larger immutable SST file. And then after enough of those files build up, they also may get compacted into one larger file. And this can continue. You see that in this scenario, the bulk of the data is in this, this large SST file that essentially represents the oldest data that's in the database. These will eventually be included in these background compactions, but it will be fairly infrequent, and that's by design, in order to prevent us from compacting too much data too frequently. Also of note, these compactions are also responsible for garbage collecting old tuples and old versions, which I'll touch on again shortly. In addition to background compactions, we have what's called a full compaction. And so what that does is, rather than simply including the files that meet a certain size criteria, instead this will include all files in the RocksDB instance, i.e. tablet, and compact it all into a single file. So as Yugabyte is an MVCC store, we store our deletions as tombstones. So essentially, when you delete a tuple, what you're actually doing is inserting a tombstone, and that tombstone then makes it so that when we look up that tuple, we recognize that that tuple no longer exists, and we return appropriately. In the anatomy of a tombstone is essentially just like a regular tuple. So the key matches that of a normal tuple, but the value of the tombstone is what indicates that the tuple is deleted and no longer has data. So the motivation behind this project, so I'm going to give an example. So let's say we have a table of jobs, and you've got a job ID that is the primary key and then a few columns afterwards. And let's say that primary key is sorted on job ID ascending. So we put 1,000,000 rows in this table, and then we delete 100,000 of those rows. So let's say that those jobs have completed, and once the job completes, we delete those rows. So what that looks like under the hood is essentially you have all of those tuples inserted. We then delete those tuples, i.e. insert tombstones for 100,000 of those tuples.
And maybe I'll just make one or two comments. So firstly, there are two reasons why we don't delete the tuples in place. One, like John alluded to, is that Yugabyte is a multi-version, uses MVCC. And so there could be, this helps reads not having to take locks. And you can read, an active read can still read the old version of the data, while a newer read has to not see that data. So we record the delete as a tombstone. The second reason is also Yugabyte is a log structured storage engine. So the actual reclamation of space for deleted tuples happens in the background in compactions, right? Now, sometimes when we talk about tombstones, for those of you that might be more familiar with Apache Cassandra, there is a concern that comes saying in Cassandra that because the tombstone itself is replicated across the peers using eventual consistency, there are some additional safety things that people have to configure, what is the garbage collection threshold for delete tombstones and so on. Those equivalent issues do not arise in Yugabyte. Yugabyte uses a strongly consistent wrapped-based replication. So just like an insert of a record is wrapped replicated, a delete tombstone is also wrapped replicated across its peers. So those kind of inconsistency issues of potentially deleted values resurfacing do not appear in this architecture. So I just thought I'll take a few minutes detour to cover those aspects, John. Thank you.
Yeah, no, that's a good point. So examining how the data is stored under the hood, let's look at what different queries might do with this data. So if, for instance, you are doing a point lookup on this table and you're asking for job ID equals 1, you can see that this is not really a problem. Essentially, what we do under the hood is we look up the latest version of job ID equals 1. We see that it's a tombstone, and we return that no rows have been found. So not a problem. The only thing that is really an issue there is essentially that there's a duplicate of the tuple in the tombstone, and when that could eventually be removed.
Yeah, basically, in other words, for point lookups, these tombstones don't really affect performance. Yes, they're taking up some space you will not yet reclaim the old space till compactions happen, but it's not affecting performance, at least. Yeah.
Right. Yeah. So in the case of, say, a range lookup, that performance impact gets a little worse. So if we're looking up all tuples with job IDs between 50,000 and 150,000, in this case, we have to look up all tuples in that range. Half of that work goes towards looking up tombstoned tuples, that aren't going to appear in the result. But the end result, looks like maybe I messed up that slide. The end result, though, is that we return that 50,000 tuples exist, and we only return this quantity. So essentially, we're only having about a 2x read amplification as a result. No, that's the so in this case, we're returning half live data and half tombstone data, meaning that we return 50,000 rows total.
That's right.
Where this gets really bad, however, is if you have a query like select, order by, and limit. So in this case, let's say we're trying to find the earliest live job ID. And again, remember that this table is indexed on job ID. So ideally, this would be no problem and just a point lookup. What happens in practice, however, is that we first look up job ID of 1, and we see that job ID of 1 has been tombstoned, at which point we have to go back down to the storage level and look up job ID of 2. And you can see we have to go back and forth again and again, leading to essentially 100,000 lookups to find that one single tuple, which obviously has quite a bit of read amplification associated with it.
Yeah, basically we kind of start the seek at sort of minus infinity because we don't know what the smallest job ID is. Is it like, minus 15 or 0 or 1? We don't know the domain, right? So we kind of start the search almost like at the smallest possible value for that data type. But we unfortunately encounter a lot of tombstones in the sort order and the first valid tuple just happens to be 100,000 records away, right? And now you can suddenly see that how range scans, essentially this query has to do a range scan till it finds the lowest valid job ID. And we can start to see how delete tombstones can affect performance until compactions happens, correct? So John, go ahead, yeah.
Yep. And so the solution to this problem is essentially the notion of a smart full compaction. Essentially, when we detect this problem, we recognize that, okay, it's time to compact this tablet.
And just to be clear, like essentially, this doesn't really require any change from an app developer's perspective. We are just, in addition to taking size-based hints or time-based hints into the compaction algorithm, we are automatically now, this project, what it does is it takes these kind of aspects into consideration and automatically scheduling compactions when necessary. And John will kind of cover, what those details are.
Yep, exactly. This is something that as an app developer, you can just set it and forget it. So the basics of this feature is essentially we add 3 new statistics at the DocDB level. So we keep track of the total number of keys that we find. So this is any key that is read by any query gets included in this statistic. We also keep track of the number of obsolete keys that we find. So these are any tuples that we read and determine are either tombstoned or have been expired via TTL, and thus are no longer valid. And we keep track of a third statistic, which is this obsolete keys found past cutoff. So this one's a little bit trickier. Essentially, we keep track of a certain amount of history in the database as an NVCC store. So this is for like transactions or for point-in-time recovery. We keep track of a certain amount of history. And any information, any data that is still within that time period cannot be included in a compaction. Cannot be removed in a compaction. So essentially what we're saying here is let's keep track of all obsolete keys that we find that also, were we to run a compaction, we would be able to remove those obsolete keys. And just for everyone's knowledge, that time period by default is a 15-minute retention window. So essentially, what we are looking for in these statistics is we're looking for the ratio of obsolete keys past the cutoff that we find over the total number of keys found. So this essentially gives us a ratio or a percentage of what percentage of the reads we're doing on this tablet are essentially worthless reads. They're just reading obsolete data. And we keep track of that information over a window of time. So by default, we keep track of this over a 5-minute window. So we evaluate that ratio of obsolete keys over total keys over that window of time. And if we detect that the ratio and a couple of other factors meet the criteria, then we trigger a full compaction on the tablet. And that window is a sliding window of time. So essentially, by default, we evaluate this window every minute and just shift the window by 1 minute each time we evaluate. So here are the TServer flags that we use to control the feature. I'm going to spend a minute on this slide just to explain what the knobs we have are. So the interval, i.e. the period of time in which the window slides, is controlled by this check interval second. So this is the frequency with which we check the ratio. The default is 1 minute. We can also control the size of the window. As I said, the default for that is a 5-minute window. The percentage obsolete, so again, this ratio of obsolete keys versus total keys, we set to a default threshold of 99%, which is quite high. However, this will cover the most egregious cases. Again, the example that I gave earlier doesn't seem too far-fetched, and that was well over that 99% threshold. So we anticipate that this will trigger most of the time there's a significant problem with read performance. We also include a minimum number of obsolete keys found. So essentially, we don't want this to be compacting if like 1 out of 1 reads was an obsolete key over that 5-minute window, then that's a pretty good indication, or that's not a good indication, rather, that we should compact at that point. And then we also include this additional flag, which is turned off by default, but essentially you can put a minimum wait time between these full compactions. So if, for instance, you're generating enough obsolete data that that you are triggering these compactions every 15 minutes or so, you can potentially add additional wait time between those compactions so that you're not constantly running full compactions. So re-examining that same example from before. So again, we look up the earliest job ID, which we only know of as job ID equals 1. We see that that is obsolete, and so we increment both statistics, the keys found, and assuming that this tombstone is past the history cutoff, we also increment the keys found past cutoff. And so this continues as before. Again, we have to do those 100,000 reads in order to find a single key. However, this time we've incremented these statistics. And so the next time that window slides and we reevaluate the ratio, we'll determine that a full compaction is needed on this tablet. And then once the full compaction runs, everything will be pushed into a single file. Those tombstones and the tuples that they delete will essentially cancel each other out, and we will have a file of only live tuples. So Future reads won't include those tombstones, again, until more are written, inevitably. So from there, I was going to go into a demo unless there are any questions about the feature so far.
No, I think a demo sounds good.
Okay.
In fact, I just saw a comment, so maybe I'll just share that. So the comment was, we have this exact situation and now have cron jobs running daily to call table or index compactions. And this will give us a data-driven solution instead of guessing with a cron every X hours. So yeah, thank you, Joe. That was exactly the motivation for the feature, because people were having to work around it by manually calling compactions on tables that had a lot of deletes happen. One additional advantage of this I would call out is you don't even have to compact the entire table. Maybe your job ID table had like 100 tablets, but maybe only the leading few tablets in the sort order had a high number of deletes. So this mechanism will just sort of automatically recognize the tablets that will benefit from it, and it kind of avoids unnecessarily compacting other tablets. Go ahead, John.
All right. So just to show, it's a good start. Oh, so we have a table, jobs, that is exactly the same table that was discussed in the example. So if I, at the moment, I haven't deleted any tuples on this table. So it still has those 1 million rows in it. So if I do an explain analyze to get the top job ID, you can see that the execution time took sub 1 millisecond. And I'll run that again without the explain analyze, just to show what still exists. If, however, I delete 100,000 tuples from this, I should also note this is only running on a single tablet just for simplicity, but this is the same process that would run writ large in a much larger cluster. So now I've deleted 100,000 of these records. If I do an explain analyze again, you see this query now takes over 200 milliseconds. And if I were to have deleted more, it could take as much as over a second. And I can show you if we run it again and again, same thing happens. It still takes over 200 milliseconds. Now, for this particular cluster, I've narrowed these, I've reduced these flags considerably just for demo purposes. So I've got a history retention of 60 seconds, meaning that these reads that I was doing earlier will not actually trigger a compaction because it was still within that 60-second window from when I ran the delete. So those deletes are still live. The window is only a 20-second window, again, just for simplicity of the demo, and the obsolete keys found is also drastically reduced.
Yeah,
well,
just to call out what John is doing, like, see, for the purposes of the demo, he kind of deleted 100,000 jobs instantaneously. But in practice, workers will come, they'll dequeue jobs, they'll do their own processing, and they'll delete the job. So the deletes tend to be staggered over time. So our default flags of how aggressively we react to this situation are a little bit more conservative. For the purpose of the demo, since we're trying to show that in a matter of minutes, he has set the flags a little bit more aggressively.
Yeah, that's a good point. This is just trying to compress a real world workload into a demo period.
Yeah.
So I believe we are past that 60-second window from when those deletes took place. So when I run this, this query again, where essentially we're getting the first job via that index on job ID, you can see this still took over 200 milliseconds. Now, in practice, if I look at the TServer logs, what we should see happen quite quickly is now this tablet has become eligible for compaction based on document key access statistics. Percent obsolete 100%, it's 99.999 or something like that. And the total keys seen is over our threshold. So what will happen as a result is we'll create a compaction. So this indicates that the compaction has already executed because the data is quite small. So scheduled full compaction is what indicates that it was compacted by this feature. And so now, if we go back and we run the same query as before, now we're back to getting sub-millisecond response execution time on the same query. And again, this all happens behind the scenes. For the purposes of the demo, I adjusted the default I adjusted the parameters from the default, but in a real workload, this will all happen automatically, and the flags are set such that you don't have to worry about them at all. So there are a few future improvements that we're looking at for this feature. So one is that there are other scenarios that may indicate that a full compaction can be helpful for read performance. For instance, there are some scenarios where repeated updates may not be captured by this new statistic. And so in those cases, we may want to add some other ratios or add new statistics or roll them into the existing statistics that we've created here. I mentioned that 99% is quite a high threshold that was intentionally set to be quite conservative. We believe we can set this to be less conservative without risk of overcompaction. Say like 90% should still be quite high in terms of the amount of obsolete keys that we're encountering. And so we believe we can safely reduce that default threshold without risk of overcompacting. And again, like any user could set that to a lower threshold, but by default, it's set quite high. And then another is an option to compact on replicas too. So currently only the leader tablet as well as any read-enabled followers will be compacted. And that's because essentially you're only generating these statistics if you're doing reads on the tablet. However, so this is both a positive and a negative. It's a positive in the sense that we're not compacting follower tablets that we're not reading from, which means that we're not doing compactions that the user isn't seeing any benefit from. However, what it also means is if we have a failover to one of those followers, it will mean that it may require additional slow reads before it detects that, hey, we need to do a compaction on this new leader, at which point, so performance may drop for a bit until that compaction is triggered, at which point it'll return to what it was before.
Yeah, just to put a finer point there, it's a trade-off, as you can imagine. Basically, what we're doing is, since these metrics to detect whether we are stepping over a lot of deleted tombstones are tracked on a tablet basis, the tablets from which you're reading, like maybe you're a strongly consistent default, so you're only reading from the leaders, or maybe you have follower reads enabled, so you're reading from followers. So only the tablets which are in this read path and encountering this behavior are scheduled for compactions, which means, like John said, if you have a leader failover to one of the peers, it will have to go through this smart compaction cycle once before it starts to get the benefit. But it may so happen that just its natural compactions itself might have caught up, right? Because maybe independent of this feature, there is a natural compaction frequency that happens when enough new data comes into the system. But if it doesn't happen, then the tablet to which we fail over has to still undergo this automatic learning cycle, and you could experience a small delay or drop in performance. Still, its compaction happens, right? But that's a trade-off. Like you can do more work upfront for less benefit versus this approach we have taken for now.
Yeah, and ideally you would have the option to choose between the two, but for now it's only any tablets that are actually servicing reads. So just to explain where the feature is available, it's available on 2.18.1 and any version past that. Obviously available on the latest as well. The stats that we added are available in 2.14.11 plus and 2.16.6 plus. So while they won't trigger automatic compactions, what they will do is you can look at those stats to see if this feature would be helpful or determine if it would be useful to trigger a full compaction manually to improve performance. Yeah, and thank you for the talk, and if anybody has any questions, happy to take them.
And actually, you just answered the question that came by, like what versions of these, what version are these features released in? Yeah, I think the short answer is it's 2.18 because the statistics are still kind of low level. I mean, I know some of the power users are going to make use of it, and it's nice to have it there. But yeah, the feature is available in 2.18.1. There was one other question. Let me just read through it. If we want to compare the particular values of a field from one data set to another, how can we check out the duplicates and how can we remove them? And also, how can we look up to get that particular field of related data set from the second data set? I think this question seems a more generic kind of SQL question on like how to do set difference between two sets, but we may not be able to cover it in this tech talk. Probably just I would encourage Ishwar to post this question in the community Slack channel that you see the link to on this slide, so that we can have somebody address it for you. Thank you so much, John, for an excellent talk. And thanks all who joined this session. And see you next week on another interesting topic. It's if I recall, it's going to be about a flavor of sequences that we are adding that can especially help connection startup performance and especially so in multi-region deployments, right? So yeah, come check us out, check that talk out next week. So thank you, John, and over to you for any closing words.
Thank you. Yeah, no, that's it for me. Appreciate having the platform.
Wonderful. Thank you. Thanks all. Have a great rest of the day and weekend.